Now, this is the main plant for this building. She's right here. And what this is showing us is the temperature flowing in the clean water supply to the air handling units. You've got a supply and a return line. They're the two secondary pumps, pump 1 and 2. You've got heat exchanger 1 and 2, heat exchanger 1 and 2, and you've got 3 pumps pulling water from a well, okay, which is probably over 200 feet away. Okay. We can monitor the temperatures of the heat exchangers. We can graph the temperatures. This is just over a 6 to 8 hour period. We can actually save and recall up to a year's worth of data. So for instance, we can go to the last month and that will give us those temperatures for the heat exchangers for the last month, which is a great maintenance tool. We can actually look at the performance of the heat exchanger temperatures. If the heat exchangers start getting dirty, these temperatures should go higher, okay? And this tool is a very, very good service tool. A few weeks ago we installed a special bacteria eating system which stops the heat exchangers getting dirty. And this was just installed a couple of weeks ago, and it's already showing temperature drops over the previous month. So it's working quite well at the moment. So that's that. We have an over temperature shutdown on this system. So if the temperatures of these heat exchangers goes above 110 degrees, the whole system shuts down, and that's to protect the pipework, the plant, the equipment. If the temperatures start going above 110 degrees Fahrenheit, these pipes could actually melt or deteriorate. So we've put an alarm point and a high temperature shutdown into the programming of this system. We'll go back to the individual units. Okay, so at the moment, this system, grey means that the system is switched off on a time schedule. Okay, so grey means it's out of normal working hours. What we can do, we can go into any unit. This is a typical graphic for a unit. We're measuring supply air temperature. We've got a set point. We're measuring return air temperature. That's the actual. We've got a variable return air temperature that's we can reset. We've got an actual return air temperature. We've got supply fan speed, cooling stages. These are the temperatures that are coming out of the heat exchangers, as we just showed you. We've got static pressure, meaning if any of the VAV boxes are closed, that this unit will not run and blow the ducts. That's a protection in the control loop. And here we can actually adjust the time that this unit comes on. At this moment it's coming on 4 hours, 4 times a day. 3 hours, 4 times a day, I apologise. So this unit is actually scheduled to come on for 3 hours, 4 times a day. At this moment it's Thursday, and what we can do now, we can actually bring this unit on. That's how we adjust the time schedule. We just go, we're going to bring it on for an hour. At this moment it's scheduled to go off at 11 o'clock. 11, let's see, what's this? 6, 7, 8, 9, 10, 11. It went off at 11 o'clock. So we're going to put it on for an additional hour. So we go to the day, which is Thursday. We drag this for 1 hour. We go OK. It registers the time. In a second this is going to go occupied. We'll see that in a second. It takes up to 2 to 3 minutes. And this unit will start to go on a startup cycle. It takes 2 to 3 minutes for that to happen. This is just gone to occupied. You see that? In a second, this supply air fan speed will start changing percentage-wise, and these cooling stages will start to switch on 1 to 6. Supply fan speed as slowly, as you can see, this is the supply fan speed, has run up to 64%. It will get up to 100%. The cooling stages will start to switch on 1 to 6 stages, and you'll see these segments of blue. That's telling you the number of cooling stages that's on. And then you also see the static pressure will start to go up, and that means that's the amount of pressure in the duct because the fan has started to run. And then this supply air temperature should start to drop as the cooling stages start switching in. Fan speed's gone up to 66%. Static pressure has gone up to 0.3 inches of water. And the reason we've put variable speeds drives on each fan is because if we take 10% off the speed of the motor, actually between 5 and 10% off the speed of the motor, we're actually saving 50% energy. So that was the reason. See, the fan speed's gone up to 70% again. And before, these fans would just switch on 100%. Now we're actually staging them on. They ramp up very slowly, and that in itself is saving anywhere between 15 and 30% of energy on the motors in this unit. As you can see, fan speed is running up to 72%. We'll start to see one stage of cooling come on very shortly, and then it will go through its normal stage cycle. We will also start, as soon as the cooling stages begin, we'll start to see that supply air temperature drop. And we should also start to see the return air temperature drop. The whole staging takes anywhere between 10 and 15 minutes. Now you can start to see that the supply fan speed has gone to 77%. The first cooling stage is on. That means the first compressor's on. And then we'll start to see this supply air temperature drop because it's getting colder, it's starting to cool the discharge air temperature. As you can see, it's a very slow speed up, which is saving energy. Every time you slow that fan down, it's saving a lot of energy. Also in these graphics, we're monitoring the outside air temperature, the current outside air temperature, and we're monitoring the current outside air humidity. As you see, this temperature's dropped slightly. It's a very slow process because we don't want to shock the building. We go back to the front graphic. As you can see, this is the only one in green, meaning this unit is running. All the other units have been shut down in this building. So this building is really saving a tremendous amount of energy right now. Prior to us coming into this building and doing an energy audit, all of these units were running 24/7. There was no control on them. Some had small time clocks, but the time clocks had been tampered with. No one can tamper with this system. The tenants can't tamper with it. The building staff can't tamper with it because it's a security access system. I'm going to go. Let's just go back to this graphic. Our fan speed is getting up to 87%. Once we get up to 100%, we'll start seeing the second stage of cooling. But while that's happening, the static pressure is also rising. The supply air temperature is dropping. It would take a little more time for the return air temperature to drop. While we're doing that, we're going to go to the electrical monitoring. And with this system, we're actually monitoring the incoming supply. This is giving us, in fact, let me just make an adjustment here. This is giving us the energy usage over a week. So if I go into this particular week here, this is from the 18th of August to the 25th of August. And we can actually see how much energy is being used on a daily basis. What we're going to show you here is the average base load at the moment is 3,000 kilowatts. A couple of issues here where they were running plant 24/7. There was a reason for that. But if you look at the average base load, it's 3,000 kilowatt hours. If we go back a year, because we can go back a full year here, you see the average base load was 4,500 kilowatts. So we've actually gone from there to here on the base load. So we've saved all of that energy there. And in the daytime load, the average kilowatt hour was around 6,000 a year ago. And if we go back, go forward a year, we're now looking, the average is actually 4,800. 6,000 is where, but we've saved all of this energy. This is now no longer wasted energy, it's saved energy. And one way of giving another example of the energy savings here is by looking at the utility cost. And if we go back a year, the average utility cost was around $60,000. We started installing the system in October of 2012, and as you can see, the energy just kept dropping as we were performing the work. And if we come back to this year, let's go back a few months. We were originally up here with the average bill, $60,000. This is dollars per month. As you can see, we're not even going over $50,000. $50,000. And these are peak times, peak summer times. The average of this building is going to be around $40,000 a month. So we've taken an average of $20,000 a month off the energy usage of this building, which is around, it's over $200,000 a year savings. And that was a $600,000 investment, which means they're going to get their investment back in less than 3 years. And that doesn't include energy increases in energy tariffs. We can do the same for, we've got kilowatt hour graphs, we can kilowatt hour graph, we can carbon emission graphs, so we can get a full spectrum of savings and measurements in real time. We can generate a report for the building. We can actually do a multi-year comparison. So for instance, if I wanted to do a multi-year comparison for cost, we can do, this is 2012, 2011, 2012, energy cost savings 2013. And we can do that very easily now. We can generate these reports to the owners, we can generate these reports to the tenants, and we can generate these reports to any accountant that wants any verification of how this building's been performing. And again, we can do that. This is cost, multi-year cost comparison. We can do the same for carbon emission, 2011, 2012, 2013. That's carbon emission savings. And we can do it for actual kilowatt hour consumption. Same thing again, 2011, 2012, 2013. So we can generate some very, very detailed technical reports. One other neat report we can generate is a heat map. And if we go into a high usage time of the year, we can now generate a heat map within the building. And the heat map has a variable temperature display based on kilowatt hours. So as we go through the colour spectrum, obviously red is high usage, so we can see the times of the day when there's high usage in the building. It's very, very useful for seeing the behaviour of the building. So as you can see, from midnight to 6 o'clock in the morning, we've got very few kilowatt hours used. And as we go from 6:30 through the day, coming towards the evening, it gets redder. Obviously there's more kilowatt hours being used. And again, as we go after 5 o'clock, it starts fading out to green again. So we've got a very, very good mapping of the building load in various forms. So we've got heat maps, we've got bar chart comparisons, we've got carbon emissions, we've got kilowatt hours, and we've got the actual cost that this building is how much this building is costing to run. You can create your own dashboards. We can, at this particular building, we can measure the incoming supply. This is the incoming supplies. We can measure the landlord's metering, meaning how much the landlord it's costing him to run his building. And we can go to an individual tenant to see how much that individual tenant is using as well. So the beauty of this metering system is we can actually proportion very accurately the cost of energy for each tenant. We can proportion the energy to what it's costing the landlord to run the building. So we can actually accurately track waste energy in this building and start improving on energy control. We can do a lot of energy control based on this system. Trend control system. This is the typical panel that we use. We ventilate the panel with a fan so it doesn't get hot inside. This is a touch panel where we can actually trend with graphs. We can do traces, which is what this is. We can do actual values. We can do numerical values. And we can do a graph format. So it's a very useful maintenance tool for technicians and for engineers to see how the building's performing. The system itself, it's very simple. We have a power supply which is backed on a UPS system, and then we have binks, and binks have the strategy for the building. The actual control strategy is built into these 3 units. So scheduling, control strategy, shutdown strategy in the case of fire, it's all programmed into these 3 units. These 3 units communicate to each floor via a twisted pair cable. It's what we call MSTP, and that's how we communicate through the variable speed drives, and each one of these controllers, which is an Echo controller, Trend Controls Echo controller, has a control strategy for each individual air handling unit. So it monitors the temperatures, it does the stop and start, and it can control the variable speed drives. And that's what this unit does on each floor for each air handling unit. That's basically the heart of the system. It's connected directly onto a network. I'm going to show you the network. The network is built into this cabinet, and if you get down there you'll see we have a network switch we have the PC, and we have an ADSL modem, and that's how we get our internet connectivity for this system. So obviously we can connect into this system from anywhere in the world and control and schedule any piece of equipment from anywhere in the world based on the access password. It's very, very secure. So that's basically the network connectivity for the system. What we've done here is we're also using what we call a backnet. For instance, this system is another vendor's system. It's not Trend Controls. And what we've done, we've actually, through a backnet IP, we've actually brought all the points for this plant into our Trend Control system and done a representation of graphics and trending. So we can trend, I think we've gone through this, we can trend every single point and show the client and the owner how the system's performing. The metering software, which is the electrical monitoring, it's a wireless system. Just log in here. With this metering system, what we have 72 wireless meters connected into all the distribution panels. We're going to see those in a second. And basically what happens is all the data from each meter via repeaters streams into this data logger, which is connected directly onto the internet. All the information is stored off-site. It's actually stored off-site in the UK at the moment. And all that information gets analysed and put into these reports. If there was an issue with this unit, with this particular unit, the data stream unit, it's backed up on a remote site. We would install a new unit and it would be reinstalled within 4 hours, 4 to 6 hours. That's in the event of a failure of a unit. So basically, that is the unit that takes all the information from out of all the wireless meters, streams it back to the internet, and pulls it back to the internet to the remote site, and then it gets represented into this format, into this graphical format. And we can do this in many ways. You know, we can look at the panels, we can represent as a typical graphical usage. So again, you can see what your building is using. And again, we can go back a year. Again, we were in the 350s, and now if we go back to today, to current, you know, we're averaging 270s, 260s. You know, we've saved a tremendous amount of energy in this building. This is the main distribution plant, 4,000 amps. This is the old metering system. This is the existing metering system that was in this building before we installed our metering. It is going to be removed. This whole panel is going to be removed. What they had to do, they had to actually do a manual read of each meter. I had to write this down and do the calculations every month, right? And these are the wireless meters. Each unit is different values. This is 100 amp, 4 wire, 500 amp, 4 wire, and so forth, 1000 amp, 4 wire, etc. Basically, it's a Rogowski coil, and basically we just clip the coil around, connect a 3-phase supply to each one of these, and that is wirelessly streaming to a repeater. The repeaters are connected and they go to the data stream, which then takes the data off site. So that's basically the metering system. It's very quick and easy to install. This whole building, I think 73 meters, was installed in 10 days, and we didn't turn any of the power off. Even the 4,000 amp supplies were actually done live. I did them live myself. So there was no interruption to power in this building at all for this metering system. It's very easy to install. It's, as you can see from the software, it gives a tremendous amount of data and information on the behaviour of the building. This is the control panel. That's the IQ controller. That's what communicates with that panel in the main control room. We have return air temperature sensors, variable speed drives. They're all Honeywell. So that basically gives us the values that the drive's running at the moment. There's our temperature sensors in the ducts. These are start and stop relays. That's how we control. Same again here. Oh, this is the staging relay for each unit. This is the different stages of cooling. Right now we're on 3 stages of cooling. So we took the existing control round and put this one in. Okay, so you can see the 3 stages of cooling. Did you see 3 LED lights on over there, Joseph? So that's showing that the drive's running at 100%. 3 stages of cooling. The supply air temperature's dropped. Remember that was in the 70s, 60s and 70s? The return air temperature's dropped. Static pressure's risen. And we're in occupied mode. So now we're going to take it out of occupied mode. And we're going to shut the system down. And we basically just do that. We've changed the time schedule. We go OK. It downloads into the system. And within a few minutes, this should all go to 0.